Ну он просто сказал, что опаздывает, да?
Миша, да.
А Миша придет?
Миша придет, да. Миша придет.
А Симон неизвестно, да?
Симон неизвестно.
Ну сейчас чуть-чуть подождем, несколько минут, может Симон придет. Обычно он аккуратный. На самом деле это для нее это просто он этим занимается, и, но, конечно, он много не знает, и что. Simon is here.
Yeah, sorry.
Okay, then we start. So I repeat as usual in order to get accustomed to the so basically what we discussed last time, we finished discussing what happens in Gaussian Rosenzweig-Porter random matrices, and then started to compare the results for Rosenzweig-Porter with the results for the critical power law bandit matrices. And what we see that in some sense these two cases, although both are non-ergodic extended, but they are very different and represent some two, in some sense, opposite universality classes. So first of all, what happens in the critical case, it is multifractality and not fractality, because the shape of f of alpha is such that the fractal dimension really depends on Q. Then the second thing is that when we consider correlation function of local density of states, it has a characteristic scale which is mean level spacing, global mean level spacing. Then, of course, it has a characteristic scale which is the total width of the band, but it doesn't have the second scale which vanishes in the thermodynamic limit. So there is only one such scale is delta, and then there is a power law with the exponent smaller than 1, and it spreads from the entire bandwidth down to delta. And this is important. This tells us that there is no definite compact mini-band in this case. But on the other hand, there is a power law, and power law usually happens from some follows from some hierarchical structure of the spectrum, and therefore we suggested that the local spectrum in case of power law banded matrices, and also for the critical point of the Anderson model, which is very similar, what happens is that the local density of states typically look like a Cantor set, but this Cantor set, of course, is not the textbook Cantor set. Instead, it is a random Cantor set. And then, if we have a device that measures locally, so we have this picture, but if we have a device that measures in all the points, in all the spatial points, then such similar spectra, but not identical for different observation points, they superimpose, and we have the full band. But this full band is such that the gaps in one point are filled by the levels in the other point, and so we don't have gaps here, big gaps here. Okay, then, and this is in contrast to Rosenzweig-Gaussian Rosenzweig-Porter, where we have a compact mini band, and then, of course, if we take a global probe, then such mini bands will be placed everywhere, depending on the observation point. If we measure simultaneously in all of them, we will have similar thing. Okay, then this is just a picture, and then the thing is how to model this picture, and this model should be such that it explains all the features that we can see in the in the correlation of local density of states, namely that there is a power law with the power smaller than 1. This is so-called Schocker-Ansatz, Schocker law. And second is that the prefactor here does not depend on the size of the matrix. So, of course, this point, which is delta, it depends on the size of the matrix. So, if I will increase the size of the matrix, then this thing will go further and then fall down. If I decrease it, it will be falling down here. So I have to have a model simple enough to be able to treat it, and at the same time explaining all these features. And what I want to say is that this model is so-called random Cantor set, and in order to generate this random Cantor set, you assume that all the spacings here are independent, randomly fluctuating variables, and which do not depend on which spacing I consider, so they are identical, independent variable, and all of them are distributed such that there is a power law in a broad interval from delta to the band, to the total bandwidth, and then of course it is cut. So this is an assumption, and then I gave some arguments that this assumption is actually a good one. So first of all, I considered the very well-known example of the textbook Cantor set, where there is first the segment from 0 to 1, and then 1/3 of this segment is removed, then 1/3 of the remaining part is removed, then 1/3 of the remaining part is again removed, and this is the textbook Cantor set. So then I put this Cantor set in correspondence with some set of levels, saying that I have a level in the middle of each wide interval. So this is just a construction, and then what I wanted to show that the spacing distribution in such a construction, it is similar. It has such a distribution function, and that is the argument why what I call random counter set is really a counter set, which is described by a certain fractal dimension, which I call ds. And so what I have to find how many spacing of each size is present here, and then simply find the probability that the spacing is smaller than something. So here there is a sum of all the instances. Here is the total sum, and then I express everything in terms of delta, and I have an expression like this. And then we know that this is an integral. On the other hand, it is an integral of the probability density from the minimum spacing to the spacing which stays here. So then I differentiate the left-hand side and the right-hand side with respect to delta I, and what I obtain, so here the power will be increased by 1, and here there will be simply probability density. So I have this distribution, which is the same that I proposed for the random counter set, but fractal dimension which corresponds to this setting, to this fractal, is is equal to log 2 by log 3. I could invent a similar fractal when I remove not 1/3 but 1/4, and then this fractal dimension will change. So then, so we sort of put in correspondence this model of independent spacings with such a distribution and the textbook counter set. Then the next thing which I want to do, I want to show that that I can reproduce this law, having this construction of levels. Now, for that I take the sum of the delta function where this EI is the corresponding level of this construction before, and then I consider the counting function, which is an integral of that, and this counting function looks like this. So the big gap in the local spectrum corresponds to plateau here, and the small gaps to little plateaus, and there is this famous picture of the counter set. So then what I do, then I take two such rows and average them by shifting this picture in the energy. So this averaging is done by integration.
Sorry, and how do we go from the, on previous slide we finished with calculating the probability of having energy space between two being like...
No, I don't go, I now, what I do now, I check that what I check is the following, that the regular counter set, the one which is in the textbook, it also gives you this this power law.
Yes, yes. I
And
understand.
this is what I want to show.
Yes, but how do
And then I will show that the random counter set gives also
Yes,
this law.
yes, I understand, but I mean, it is much more technical question. How, if you go to the next slide,
Okay.
okay, yeah, so here we finish with calculating P of delta, right? And
Yes,
now, yeah, and now the question, how from this P of delta we go to this counting function C?
I don't do this. I simply do the following. So this task is not done. What I'm doing, I am showing to save time. I am showing numerically
Okay.
numerically that
Mhm.
there is this law.
Okay, yeah.
In
okay.
principle, I'm sure this is some mathematical theorem which you can prove.
Okay.
But somehow to save time, I'm not going to this proof, and to be honest, I don't know
Okay.
of such a proof. You know, if someone of you is interested and will search for mathematical literature or will find a solution yourself, so it would be a contribution to the field. I was lazy and I did not do it. Okay, so what I do, I just do numerics. I take this thing and I take it twice. With a shift by omega in the energy, but then there is a central energy E, and I am averaging over the central energy because I don't have anything to average here. I mean, when there is a random counter set, I am averaging over the ensemble. Okay, and here there's no ensemble. There is only one counter set, and all what I can do with it is just shift it. It's the simplest way to average. And I was very surprised when I calculated this integral, and this integral is easier to calculate because the integral of delta function numerically is difficult, and the integral from step function is easy. And when I did this, I was very surprised that I obtained the power law, which is of course by 2. The exponent is bigger than in the rho by 2 because there are each c is an integral of rho over E. So the thing is that in order to get rho, I have to compute this integral for C and then integrate it twice over omega, because what I have to do, I have to integrate twice each rho is the derivative of C. And there are 2 rows, so there should be 2 derivatives of C. And since I have omega here and here, the easiest way is to differentiate with respect to omega. And then there is -4 because here plus 1 over 2 and here minus 1 over 2. So then I computed this thing, and it is there. And in the log coordinate is a straight line, which tells us that this integral is a power law, and the power of this integral is 1 plus log 2 by log 3. So when I differentiate it 2 times, I will get omega to log 2 by log 3 minus 1, because there will be two omegas layers. And so I will get this. And this is what is needed, because This is this law if I assume that d2 is equal to ds. Now then I do the next exercise. The next exercise is that, okay, I now believe that this model where level spacings are identically and independently distributed and the distribution is power law, that this model gives the same thing as qualitatively the same thing as the regular Cantor set and construction of levels in it. And now I want to check that I want to apply this model directly and compute this correlation function directly from this statistical model. So now I will be averaging. I will be averaging over ensemble. So what I do the following. I first take the Fourier transform of that. So this thing after integration over E. So when I write down this thing, there will be two delta functions. When I integrate over E, only one is left. And then I do the Fourier transform and I get the form like this, which is easy to compute. And then what I say is that the difference between two energies is just the sum of spacings. It is trivial because energy is the sum of spacing. And then this should be put in here, what I will get the product of the exponents. The product of the exponents like this. Product because this difference is the sum. And then I will have a product like this, then I have to average, since all delta k are independent, the average of the product is the product of averages, since all delta k is identically distributed, so for all k it is the same thing, so this product is simply a power. And if I denote this like G, so I have this element that determines everything. And then I have to compute this double sum, and this double sum is simply with little modification, it is the geometric series. So everything is computable, and I obtain such a formula. It is a bit cumbersome because there is a double sum, and then there is some absolute value, so I have to care about this. And then I obtain this formula. And then what I see when I inspect this formula, I see the following, that if omega is much bigger than delta, so in some sense omega is large, then this tau is small, and so I have to deal with G at small tau. But what we know the following, that if tau is 0, then it is simply an integral over an integral of the density distribution function. So the total probability is 1, therefore this G of tau equals 0 must be 1. And when tau is small, this difference is small. And if I assume this thing and inspect this formula, then I come to conclusion that if my tau is between 1 and m to minus 1 over ds, then omega is between delta and n to this power, then I can approximate this k of tau as simply real part of this 1 minus g. So you can check it, but I don't have time now to do it. And then I assume what I wanted to assume, that this is a power law, and when I assume that this is a power law, then I will find that 1 minus g at small tau is also a power law. And then everything is done. I plug this thing into here, and I have this this formula for KFT, which stands in this model. It stands for spectrum form factor of this random Carter set, and then I can do the Fourier transform, and then a Fourier transform of that is correlation function of the density of states of such random Cantor set. And if I do the Fourier transform, I obtain this thing, and also some prefactor. And what I see first of all that I reproduce this power law. Then I see that if I set ds equal d2, because in the Chalky ansatz here, it should be d2. And this is analytically shown and numerically shown. And so in order to match these two relationships, so somehow in order to bring this model in correspondence with the known result for the local density correlation function, I should assume that ds is equal to d2. Then the power will be the same. Now, simultaneously, this factor will disappear because delta is n to minus 1, and this is n to 1 minus d2. So if ds is equal to d2, these two things which depend on delta, they cancel out. And so I have the second feature which I should have, that the prefactor of this power law does not depend on n. And then there is the third feature, and third feature is that this power law goes from the total bandwidth down to delta, and this approximation is valid in this window. And here stays d2 and here ds. So if ds is equal to d2, this will be 0, and this means that what I computed here is valid from the total bandwidth, which is of order 1, and down to delta. So by one simple assumption that d2 is equal to ds, I need all the three principal features. And that makes me confident that this is a right assumption. And then Simon now seems to confirm this by direct calculation, and it is important because this is some theoretical construction with some assumption, with some pictures, but one has to do it in direct numerics without any assumption, and it seems that it works. Okay, then I wanted, and this was the last slide which I could not explain in detail last time. I wanted to give an example where everything is calculated without some assumptions like this is approximately equal to that, and then without all this approximation and tilt. And but of course with using this formula that follows from independently fluctuating delta. So then what it is, for you useful information for the future, that there is such a special distribution function which has a power law tail, and then it is cut as delta at some point. Here I have chosen such a scale where I measure everything in units of delta, therefore it is 1. Now, what is important about this distribution function, it is the following, that if I take a convolution P of delta, P of delta minus delta prime d delta prime, if I take a convolution like this, then I will again have P, the same function of delta, but only with changing parameters, because there is some parameter here which is the scale of delta. So the scale there is this function depends on delta by some delta naught. So what happens is that the function is the same, but delta naught is different. So this property that the convolution is similar to the function itself, it gave a reason to call such distribution function stable distribution. Stable because it is stable under convolution. And it looks like there is no one else family of functions which are stable against convolution. So, but we know functions which are stable against convolution. So one of them is the Gaussian function. The other one is the Lorentz function, which they are very different, but they are sharing this property. And it appears that all of them, Lorentz function and the Gauss function, they are all in the family of this stable distribution, and this family has certain parameters. So that the first one is the parameter that the stable distribution is one-sided, that it is not symmetric but maximally antisymmetric. So there are two different stable distributions. One is called stable distribution 1 and the other stable distribution 0. So they are different in how they behave at small a small delta. So the one which is with the index 1 goes to 0, and the one which is with the index 0, it goes to constant. Now, I have chosen the one which goes to 0, and then the second parameter, the most important one, it determines the tail, the power law tail. And the power law tail is if this ds is smaller than 1, then, or even if it is larger than 1, but not equal to 2, then the power law tail is 1 over delta to ds plus 1. So this is a property of this function. So this is apparently a power law, but this power is ds plus 1. Then there is a parameter that gives so-called skewness. Skewness means that if you change this parameter, this function may become like this or like this. So it is some asymmetry which this parameter, you can take Mathematica and play games and see how these functions, this is from Mathematica. Then there is another parameter that tells you that it drops to 0 at 0 and not at some constant value. So if this parameter is not 0, but let's say 5, then it would have it would be 0 at 5. And then the last parameter is this scale. So it gives you the width of all these peaks. So what is important, as I say, that if you choose all these parameters, then what happens is that the convolution gives the same function, but only with changing this scale, this last parameter. Now, one of the examples is the Lorentz function. And the Lorentz function corresponds to ds equal to 1. And we know that if you make a convolution of two Lorentzes, then you will have a Lorentz with double the width. So the width will be 2 times bigger. And this is this is an example how this scale is changing. Now, then Gauss also falls in this category, but with one exception. If Gauss corresponds to ds equal 2, and then what happens, so Lorentz corresponds to ds equal 1 and Gauss corresponds to ds equal 2. And in the case of Gauss, there is no region of the power law. Instead, from the very beginning, we have exponential e to minus s squared. So this power law, as I increase ds, this power law region becomes shorter, and then at s equal 2, it disappears completely. So the Gauss is also a stable distribution, but very special one. Okay, so then what I do, I substitute this function into this formula, and then plot it. And what I have now all the features of the spectrum form factor of return probability. So at small tau it goes to 1. Then there is a power law region with the exponent tau to minus ds. So by approximate calculation I have already shown that. And then at very large tau, it reaches and the finite bandwidth or the finite total number of levels, then there is some finite limit here. And this finite limit is given by the number of levels in the counter set, and this number is supposed to be n to d2. So this limit is 1 over m. So it is n to minus d2. So this limit is, and physical meaning of this limit is the following. So when you created a particle at some point, then it spreads, but the system is finite. At the end it will be homogeneously spread. But when the states are fractal, then they cannot spread throughout the whole available volume. Because it is homogeneously spread only over the fractal support set. And the volume of the fractal support set is n to d2, and therefore this limit is n to minus d2. Then there is some tiny feature which is also in some sense important, because when it goes down, it overshoots this limit and then goes up and only then saturates. And this overshooting happens in all the cases of return probability, and this effect is similar to the effect of echo, which I discussed for usual Wigner-Dyson random matrices. It is present also for Wigner-Dyson matrices. So this is an example where I assumed only that the spacings are identically and independently distributed. And of course the power law P of delta. And then I have all the features. Okay, then we come to new stuff. And here this is, I invite you to concentrate, because it has to do with many-body localization and the problem of many-body localization. So what I want to show that when you switch from single-body localization to many-body localization when the system is with interaction, and consider what happens in the Hilbert space, then you inevitably have to do with complex graphs instead of lattices. All these localization problems started from physics of semiconductors in the 60s or even in the end of 50s, and all that was first on three-dimensional lattices. Then people start to think over, then they found that two-dimensional lattices are also very interesting. Then they recalled that there is also one dimension, but until very recently nobody seriously thought that localization problem on complex graph has some physical meaning. Instead it has. So let us consider two very popular spin chains, which are used when people are studying many-body localization. So first one is the following. So there is an Ising model, but then the Ising model is essentially classical because all the operators commute with each other. In order to bring quantum mechanics one has to add something which does not commute with the Ising part. And this something is simply the transverse field of fixed value. But the Ising is random. So this thing is usually taken deterministic, but this field H is random. So it has zero average and certain statistics. So this is a very popular model. So the next one is the model which was discussed last Tuesday during the seminar. This is the model which Google Group modeled in the quantum qubit chip. This is the model. This is the following model. So there is S plus, S minus part. S plus flips the spin, and the S minus flips it back. So there is this part, which is taken deterministic. And then there is a random field, which is like here. So this is the simplest model of that kind, because you know the next simplification would be to add here SZ. But I didn't do.
Vladimir, I'm in principle usually more familiar with the fermionic formulation. So the second, the XY model in 1D, am I right that it's non-interacting, but in 2D there's an interaction?
No, okay. So if you would be in 1D, then this is exactly mappable onto the Anderson problem of a fermion, or non-interacting fermion in 1D, but only in 1D. If you go to higher dimensions, like 2D, then Jordan-Wigner transformation does not bring you to non-interacting fermions, because in this Jordan-Wigner transformation there is some tail, there is a particle, and then there is some tail in formulas of Jordan-Wigner transformation. If you are in one dimension, then what happens is that these tails cancel out for different particles, and so they are all along one line, and then they cancel out, and therefore in one dimension you should forget about this tail. But in two dimensions it is not, because if we are in two dimensions, then there are these tails, and they bring about some very complex interaction. So this model in two dimensions is very non-trivial, because it is Jordan-Wigner is there, but Jordan-Wigner contains such tails or some special cuts, and they do not cancel out if dimensionality is greater than 2. Therefore, interaction that appears in this model in dimensionality greater than 1, it is very non-trivial. It is more non-trivial than simply two-body interaction. So
it's non-local.
That's why they had two dimensions.
Yeah, I understand.
In order to have interaction.
So it's a non-local interaction even.
Huh?
It is even a non-local interaction.
Yeah, because these are strings. Okay, so now I want to tell you a bit of how these things are conceived. So if we have 1D for simplicity, then suppose you have a one-dimensional system of spins, And in this one-dimensional system, there are, let's say, L spins. 1, 2, 3, 4, 5, L. So in each cell, you can have, consider spin 1/2. In each cell, you have spin up or spin down. So two possibilities in one cell and L cells. So altogether, 2 to L possibilities of different configurations. And any such configuration, any of these 2 to L is called bit string. Now, what is the Hilbert space? The Hilbert, since there are 2 to L, such bit strings, let us do the following. Let us produce a collection of nodes, a collection of sites, which number is 2 to L, and each such point will correspond to a bit string, to a certain bit string. Now we recall that if we have a cube, then there are in this cube there are 2 to G vertices. So in three-dimensional cube you have 8 vertices. In two-dimensional you have 4. So I can first, for simplicity of having picture in mind, I should first invoke L-dimensional hypercube. Then each such bit string will be a vertex of this hypercube. But then this is not a Hilbert space. I mean, it has only the correct number of nodes. But in fact, what we have to do, we have to connect these nodes. And when we connect, we construct a certain graph. So depending on how we connect these things, the graphs will be different. So what means connection? So each node means such a bit string. What means connection? Connection means the following. Suppose I take a bit string and act by a Hamiltonian, whatever is it, to this bit string. So what comes out after this action, I will produce a number of different bit strings. And so you see what happens. I take a bit. I take a bit string, and then I act by the Hamiltonian, and I produce a number of different bit strings. In this case, 3. Then I can act second time, and then I produce other, and so on. So in this process of applying the Hamiltonian to a bit string, I produce links. So the link is what kind of bit string I obtained from the given one by applying the Hamiltonian. And the simplest thing is this model. But let me, before coming to discussing these two models, let me first define something. And this thing is so-called Hamming distance. Hamming distance is the following. So suppose you have a bit string. And let's say like this. And then you have another bit string. Suppose it is like this. Now, I can obtain this bit string from the first one by flipping these two spins and flipping these two spins. So I didn't say it correctly. So I can produce this bit string. From that bit string, just flipping this spin and this spin. And then I produce this bit string. So I have to flip two spins in order to come from this to that. If I take an arbitrary bit string, it might happen that I have to flip all these spins, or some number of them. And by definition, the distance between such nodes in this configurational space is the number of spins I have to flip to come from one node to the other. So it is how many spins I have to flip. And this is called Hamming distance. Now, let's go to this Hamiltonian. First one to this one. So when I apply to a bit string as z, nothing happens. It is only some factor appears in front of the wave function. But when I apply Sx, I will have a flip. So, but you see here, when I apply this Hamiltonian to any bit string, I'm able to flip only one spin. This spin can be at different points, because here there is a sound. So I can flip a spin here, but only one. So then what I can say that when I apply this Hamiltonian to a bit string, I have a number of bit strings, but all of them at a distance, Hamming distance 1 from the initial one. Because by this Hamiltonian, I flip only one spin. And so how to see it? So it is like this. So suppose this was my initial bit string. And what I get applying the Hamiltonian, I will get all the bit strings which are at distance 1 from this one. So I get this one, I get this one, I get this one. When I apply one time. When I apply Hamiltonian the second time, I will get this one, I will get this one, but not this one. Now when I apply to this, I will get this thing, again this thing, and also this one, because it is at a distance 1. So applying the necessary number of times this Hamiltonian to the initial bit string, I will get all of them. And so what does it mean? It means that all these things are related, because each time when I, for instance, I apply the first time, then I get this link, I get this link, and I get this link. So when applying the Hamiltonian, I'm drawing the links. And eventually, when I applied it enough time, I will have all the possible links. And this already is a graph. Because a graph, as I said, it is not a collection of points, it is a collection of points connected in a certain way. And the way they are connected depend on the Hamiltonian. So in this case, the Hilbert space is a hypercube of dimension equal to the length of one-dimensional system. So it is very high dimensional. Now, consider this situation. Initially, I have the same. Initially, it is convenient for me to think in terms of the hypercube, but it is simply to without any real connection. So it is simply to draw all the points which I have. It is not a connection, so it is not a graph. But then I start to apply the Hamiltonian, and applying the Hamiltonian, I am producing links. But you see what happens. Each application of the Hamiltonian, this part does not do anything because it is Z. It doesn't flip this thing. But this operator flips a spin down, and this operator flips a spin up. So when I apply Hamiltonian one time, I flip two spins. Not only, I flip two spins which, if it is local Hamiltonian, which stay close to each other, because this is the nearest neighbors in the space. So what I can do, I can flip these two, 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 but not this and that, because here is only nearest neighbor. So when I flip two spins, this means that I make a link which connects two points at a Hamming distance 2, not 1. So this means the following, that you need, if I take this as an initial bit stream, then what can I get? I cannot get this one because it is only at a distance 1. I cannot get that one. But I can get this one because it is at a distance 2. 1, 2. So I can have this link. Now, then I can have this link because it is also 1, 2. And I can get this link 1, 2. So I can get all these links are at a distance 2. But as I said, not all of them are produced by this Hamiltonian. Only those who are neighbor. So some of these links do not appear. Okay, and then in order to find out what kind of graph I will obtain, you see, my poor imagination does not give you immediately the answer. So you should go to Mathematica or some other program. You should learn how to manipulate with these graphs, and then you can draw the graph. But definitely it will not be a hypercube, because it is not allowed to connect these things. If I would be able if it is not the real nearest neighbors, but all of them, then all these things are allowed. And then what I will have, from this side I will have all that, and then from this side I will have this one, then I have this one, and then I have this one. So in this three-dimensional situation, where there are only three spins, it is a tetrahedron. So if I studied only two things, but then if I start from here, then I have also this link. So I will get a tetrahedron, but if I start from a different point, I will get another tetrahedron, which are disconnected. So you can see what, so you can draw this tetrahedron here. So this is what would be the Hilbert space if I do not restrict to nearest neighbors. If I restrict to nearest neighbors, there will be fewer links. But of course, this is a very simple situation where there are only three spins. If I have 6 spins, then it will be a mess which I cannot imagine. So for this reason, there is a science which is known as graph theory, because you know, when you cannot imagine something, then you should apply. You should call to mathematician and say they can operate with abstract objects. So this is how to produce the Hilbert space. Now there is a different system and a different way of creating a Hilbert space. And this system, this is an example of a Fermi seed and interaction, pair interaction. So any pair interaction, it is two creation operators, two annihilation operators. Now, suppose initially I have one quasi-particle, one excited particle. Then, if I apply such a Hamiltonian, so what I can do, I can eliminate 2 electrons when they are present and create 2 electrons when they are present. So when I eliminate, it is hole, 2 holes. And when I create, there are 2 electrons. So what I have the initial electron plus 2 electron hole pairs. So if I'm asking how many electrons do I have 3. So I had 1 and then I had 3. So how can I draw it? I have 1 electron, then I have this one and 2 others. Then I can repeat this process, and I will have a tree. So the number of electrons which appear by application of the Hamiltonian will be the number of points at a certain generation of this tree. And the fork space is also a Hilbert space, but the variables there are not bit strings, but the number of electrons in certain state. So this is, this was by Fock because it was invented by Fock but essentially it is the same Hilbert space, but only different variables to characterize it. So why I have shown that? I have shown that in order to see that when you do, when you take usual interactions, pair interactions, and apply it to a Fermi system, then you have something like a tree in the beginning. But then, of course, these things start to interact with each other, and this tree will be scrambled. So now we naturally come to graphs like random regular graph. So what is the random regular graph? It is some model of some hypothetic Hilbert space. But what is the definition of this graph? The definition is that each node is connected to a definite number of other nodes. So here, each node is connected with 3. Any other node is also connected with 3. And in the end, you have something like, like a global, but in fact there is some order here. So if you start to analyze this mess deeply, what you will see the following, that in such structure, there is almost no short loops. So I cannot, like on the lattice, I have plenty of the short loops. So I can go from here to here, to here, to here, and back. I have plenty of short loops. Here, there are almost no short loops, but the loops are present. And those loops are very long. So, first, this graph has a form of a tree. But then, since the tree grows from any side, you take another side and it will be also a tree. But if you have tree growing from any side without loops, these are not connected graph. In fact, what happens that there are very big loops, and those loops connect the trees growing from any point, and then you have the right image of what is random regular graph. So locally, if you, let's say, apply your Hamiltonian not many times, you have a tree like you have a tree like here. But when the number of excitations will be large, then there will be a qualitative change of the things, because these trees which growing from any point will in fact coming one to the other, and so these trees are interconnected. Now, you see, this is also a random regular graph, but this is how mathematics plots it. And what is important about the random regular graph is the following, that I can ask a question. How many points are at a distance at a given Hamming distance. And Hamming distance, how many times I have to go through the links from one point to the other. So the question is, what is the distribution of the number of the distribution of the distances? And this distribution of the distances you can easily find from Mathematica, and it is like this. So first of all, if a graph has a finite number of points, then there is a maximal Hamming distance. And the maximum Hamming distance is more or less the size of the loop. And it is proportional to the maximum Hamming distance is called radius of the graph, or diameter of the graph, beta diameter. And then you find that for such graph, it is logarithm of n by logarithm of k. What is n and what is k? N is the number of points, and k plus 1 is the number of links from each point. So here the number of links is 3, but k is equal to 2. So this is the maximal Hamming distance. And so if I plot the probability to find the certain distance, then it is 0 starting from a certain point because there is a maximum number. And it is very sharply peaked at some point which is only few Hamming distance from the maximum. So what you have an exponential growth here, and then a drop which is faster than exponential. It is, and actually this drop is only few Hamming distances from the most probable one.
Sorry, this is Hamming distances between the neighbors, or
no, this is the following. You take two sides at random.
Yes.
On the graph.
Okay.
And find the Hamming distance.
Okay.
Which is R and M.
Yes.
Okay.
Okay.
And then you count how many R and M are equal to 0,
okay,
1
so
to 5, and so on, and divide by the total number of the pairs, which is proportional to n squared.
So if I think about our previous models, like Ising spin chain or XY spin chain, this graph is some subset of the whole.
For the hypercube.
Yes, this is AE.
For the hypercube, this graph looks like that. It is symmetric. It is symmetric over R by 2.
Yes, I understand, but I mean like this random regular graph, it is some kind of subset of this hypercube, right?
It could be,
okay.
Yeah, it could be viewed like that.
Okay, thank you.
Because I said for simplicity, because we have 2 to n points, I first draw 2 to n points arranged in the hypercube. But this is not a graph because
yes,
for
exactly.
the graph you have to connect them.
Yes.
And each graph like this will be a subgraph of the. Okay. So what we can learn from here? We can learn from here that the most of the distances are very close to the diameter, and therefore, like a physicist, like not mathematician, I imagine this random regular graph in the following way. So there are from each point a tree is growing, and there are sides which are arranged as a tree. But then you face a loop, and then no longer tree structure is valid. And those, since the size of the loop is of this order, then I can roughly say that there are two types of the sides. So from each point the tree is growing, and these sides I call tree sides. And so this tree persists up to almost up to diameter. And then there are plenty of the points which are all at a distance almost equal to diameter, because it is very narrow distribution. And these sites I call hollow sites, so remote sites. And this is important for me. Why? Because now I want to do the following thing. So why I was telling all that? I was telling all that because I want to have some reasonable mapping, not mathematical mapping, but mapping, physical mapping from the graph to a certain Rosenzweig-Porter matrix. And how to do that? First of all, on each graph, and for instance, on this RFG graph, I can compute the green function from this point, let's say, to that point, 2-point green function. And this 2-point green function, when averaged, it depends only on the Hamming distance. And to compute it, you have to work out, you have to consider the local structure. For the case of the tree, it is a simple structure because there are no loops on this way until you come to the size of the radius, of the diameter. But for instance, for the lattice, which is also a graph, it is not so simple because there are plenty of small loops. Okay, so you can find the green function. So how you find the green function? We usually, since there is hopping only to the nearest neighbor on the graph by construction of the graph, then to find the green function from between this point and that point, you have to take high order perturbation theory. So you have many hops, right? So when you do this high order perturbation theory, you essentially do the product of green functions between these two sides, and so on. When there are no loops, it is just one product. And this is a simplicity. If there are loops, then there is a sum of the products, because there are several passes from one point to the other. Okay? And that's why it is difficult to compute the green function for instance, if I want to compute the green functions from here to here, so there is this path, and it gives you the product of green function here, here, and here. Then there is this path, which also gives a product. Then there is the path like that. So there are plenty of the passes. And all these passes gives you some amplitude. And these amplitudes, by rules of quantum mechanics, they have to be summed. So for the tree, you have one path only, no loops.
But we can go, even on the tree, we can go there, forward, then backward, then forward.
This we can do. We can do, of course. There is.
So what is that?
There is a going. No, if it would be simply like I said, then the problem would be just, write down immediately. But in fact, it is not an easy problem to compute the green function, even if there are no loops. So, but this is a dramatic simplification compared to the lattice, for instance. Now, so likewise or otherwise, you compute the green function. For the tree, it is the problem of mathematical physics, and you can do it. So you can do it, for instance, using. So then you have to average, you have to find moments of this. So it is some mathematical problem. Important, but the physical idea is the following. So you have all the sides arranged in such a way. You take some side, then for some while, for some distances, Hamming distances, it is like a tree. But then you meet a loop, and this, and you come to this hollow side. So now, so I divide all the sides by two groups. One of them is the tree, and the other is remote sides. And the green function, and I pretend in this way that while I'm computing the green function, I can forget about loops. But then what I do, I replace the orthogonal matrix element by the green function, because the green function is actually the transmittance from one point to the other. So it is many-step transmittance, which is computed in Hyoudov perturbation theory or non-perturbatively. So what the idea is that since all the so the first idea is to replace instead of diagonal matrix element to put green function, but not simply green function. Put the green function over the majority of the sides. So so the green function at a distance equal to diameter. The majority of the sides, I at the distance of the diameter. So I say that all the points here, all the matrix elements, and the size of the matrix, it is the size of the remote sides. And so all the sides in between, which are the three sides, they simply amount to compute this green function, and this green function stands here instead of the matrix element. So there are two steps. First step, you forget about loops. You compute the green function. And then you compute it at a maximum distance where you don't see loops. And this distance is the diameter. And then you construct Rosenzweig-Porter. Why Rosenzweig-Porter? Because the variance and the statistics of any green function, it depends only on the Hamming distance between this point and there. And if I say that I'm considering only points at a distance equal to diameter, and this is the majority of the points, then the moments of this green function, which is the moments of H and M by my construction, all these things will depend only on R. So they will be all the same in this matrix, because I take only distances almost equal to R. And so this will be indeed Rosenzweig-Porter, because all these matrix elements will be given by the green function at a distance R, and this means that all of them will be the same. So the statistics of all matrix elements is the same, except for diagonal one. And diagonal one is just given by on-site energy. So each in all these models there is an on-site energy, and it fluctuates somehow, and this gives the diagonal. Okay, and then if I have this moments, I can invert the moments by Milan transform and get the distribution function of the off-diagonal matrix A. And what is important for the tree when I compute this green function along the tree, then I can do it exactly. And it looks like this. The moment looks like big number r multiplied by a certain function of this of the number of the moment, so of the order of the moment. And this certain function is the main ingredient of the theory. And it was, for the tree, it was considered long ago by Abu Chakra, Anderson, and Townes. And it was found that this function has, it is almost quadratic function of beta, and very special one, such that there is only one parameter here. So usual quadratic function has 3 parameters, or at least 2 if one of them is comes to the prefactor here. But here there is only one parameter. And the most important thing is that this function is symmetric with respect to 1/2. So this function beta for the tree, it looks like that. This is beta, this is epsilon of beta. It looks like this. This is 0, this is 1, and this is some minus, sorry, this is 0, this is 1, this is logarithm of, and this is some minus c. So it is not exactly parallel, but it is very close to it. And but the symmetry, this symmetry with respect to 1/2, it is exact. So one can exactly find this function. It is not a simple one, but it is close to parabola, and it is symmetric with respect to 1/2, and this is exact. And now what you see is the following. So if you have this moment like that, so what you have to do, you have to plug it into here, and then compute this integral. Since there is a big number r, you compute this integral by a saddle point approximation. So you just find the stationary point and find this function. Since it is this is a parabola and this is a linear function, so it is easy to find the stationary point and then compute the distribution function. And this distribution function, it will be like this. So why like this? Because here stands, sorry, I have missed here logarithm. Here there should be minus 2I beta logarithm of this. This is the main thing. And then you differentiate with respect to beta to find the stationary point, and this stationary point will depend on logarithm of h, which is missing here. And then you find the stationary point, plug it again here, and what you have, you have a logarithmically normal distribution. So, so what happens is the following, that you have a logarithmically normal distribution, but not an arbitrary one, the one in which the variance, so this is square of logarithm plus constant, and this is the variance, and this is the shift. Logarithm can be positive or negative, therefore it is a shift. And you see what happens, and what is this shift? This shift is simply, this is minus logarithm of the typical value, because somewhere this this thing becomes zero and becomes it becomes zero at h typical. So this combination is just logarithm of h and m divided by h typical and m, and everything squared. So I can, and if h is equal to h typical, then there is logarithm of 1, this means 0, and this is the maximum of this function. So what is important here is that the logarithm of the typical value and the variance differ only by a factor of 2. So in principle you may have, you may have you may have something like that. So this is the logarithm of distribution function, this is logarithm of h and m, and so you have the typical value where the distribution function is maximal, and then you have a width. So you have two parameters. But for the tree, green function for the tree, because of this symmetry, about 1/2, this symmetry dictates that the shift, this thing, and the width differ only by a factor of 2. And this is the specific symmetry of the tree, which is also the symmetry inherited by random regular graph. So it is only for this particular graph that it becomes like this. Other graphs could have different distribution function, but the method is general, in fact. So what we obtain that a complicated graph, but with short range hopping, so there is no hopping like this directly, it is only through short range hoppings. It is equivalent to Rosenzweig-Porter ensemble, but the distribution of diagonal elements are strongly non-Gaussian. Because logarithmically normal distribution, it doesn't have, it have all the moments, but moments starting from some number become growing with them, become growing with this R. And R is logarithm of n. So this is strongly non-Gaussian function. It is Gaussian in the logarithm, but not Gaussian in this thing. So it is a function that has important tails. And this is the general thing. So the general thing is that the Green's function on structures like that, they are very broadly distributed. So in this case, they are distributed logarithmically normally. And this is the message. So what was done by Mark Kravtsov already in 2023, but then a bit more detailed on this picture, which I guess is not published. This is the distribution of the logarithm of the Green function at a distance which is something like half of diameter, and for the real complicated spin system. So it is more complicated than the one that I have shown. So numerically, you can find this Hilbert space. You can compute the distribution of Green's functions at a large distance, and this distribution and plot the things that is the log plot of this thing and as a function of the Green function itself. So it is a plot which is like this, and we see at least qualitatively it is a parabola, and the maximum of this parabola depends on disorder, and when disorder increases, the maximum goes to the negative value, so that the typical value is becoming very small. Typical value of the matrix elements, and the logarithm becomes negative. So you see, this is not a random regular graph. There is no assumption about regular graph. There is no assumption about this three sides and then hollow sides. It is just direct calculation, and it shows you that this is a representative example. That's why I am talking to you. So let me see if there is something. It looks like no. Okay, so let me then. Could you wait some 5 minutes? Because I want to finish this thing. So then, what you can do, you can say, well, okay. So I get a motivation why a Porter-Thomas, a Rosenzweig-Porter ensemble with logarithmically normal distribution of diagonal elements, why it is relevant, at least qualitatively, to describing interacting spin chains and the problem of localization. So what you can do, you can do the following. You can write down more general distribution, which is like this. So there is the typical logarithm of the typical value. So this sheet. And then there is a width. The width is here. So for the logarithmically normal distribution, which corresponds to random regular graph, this parameter p is equal to 1. And then there is this factor of 2, which I have been talking about. And the typical value is like in the Gaussian random matrix ensemble, it is parameterized like n to minus gamma. So it is like we did it for the Gaussian case. And now you can plot this thing. And you see that when then P is very small, you get very narrow distribution, this width becomes small, and this approach is Gaussian, but when P increases, the tails become more and more fat. So it is no longer anything like Gauss because of this thing. And then you can do the following. You can apply the criteria which I was talking about, because this criteria was not an assumption about the Gaussian distribution was not done there. So it was in terms of the average or with the distribution, whatever is it. And these two criteria we have discussed. And now what you have to do, you have to take this distribution and compute these averages. And the result is that you can find the point of the Anderson transition and point of the transition from multifractal situation to ergodic. So this is how, you see, in the Gaussian case we have this thing equal to 2 and this thing equal to 1. Now we have some dependence on this parameter that controls the thickness of the tail. But more importantly, we have some other thing, which is the distinction between the fully ergodic and weakly ergodic case. So, and we have a new transition. So, you see, the idea is the following, that the criterion of ergodicity is this one. It involves square of the average square of the matrix element. But now, when we have tails, when we don't have tails, when we have Gaussian distribution, then this average is of the same order as the typical value. But when we have tails, then the average and the typical value become very different. And this is the reason why now there are two possibilities. We may have ergodic case which is the same as random matrix theory, so all the moments and everything is like in the random matrix theory, and also ergodic case in which the moments are different. So we will come to that next time. But I tell you what is the picture, what is the difference, pictorial difference between the fully ergodic case and the weakly ergodic case. The fully ergodic case is when all the available volume is filled and is filled densely. Weakly ergodic case is the following, that not all the available volume is filled, so there are holes there. So the regions where amplitude is small. But this doesn't mean that it is a fractal, because if you have a structure in which holes are homogeneously distributed, then the volume of the field space, the volume which is filled by the wave function, is still proportional to the total volume, but with small coefficient in front. And this is not fractality. So if you have holes which are homogeneously distributed, you may have many holes, and you still have the volume of filled part which is proportional to the total volume, but with small coefficient. Fractal means when the volume of the filled part is smaller, it scales like the total volume with small parts. This is the difference. Now, to me, this, so in this case, you can find where the transition happens. The criterion is similar to that, but instead of the average, we have typical average. Now, what I want to say is that there is another direction which I do not touch. This is for Simon. That one can ask a question: what will be the ETH? So the eigenfunction thermalization hypothesis. So what happens to E when you come from this case to that case? So this is the like random matrix. So this means that you can everything described using the random matrix and ETH included. But this is not non-ergodic case. But still, this is not non-ergodic case. This is an ergodic case from the point of view that the fractal dimension is 1. But ETH will be different. So because it is no longer like random matrix theory. And what I think it is an analog of what Lev did in the quantum sound model, where they found some onset of deviation from in ETH from the canonical way. So I think that it is exactly this difference between this phase and this phase. And in the log-normal case, log-normal Rosenzweig Porter, you can model this thing and you can study it also analytically. I didn't do it for the perspective of ETH, but it is interesting to do it. It's interesting to compare what happens in the quantum sound model in this famous paper which Lev has published, and you also were present there, right?
No.
Okay. Anyway, and this